Hi everyone, I'm Jonah Rose. I am a graduate student at the University of Florida, and I've been working here this semester with Paco, developing what we're calling the Dark AI project. So I'd just like to start off by thanking Paco and then some of the other collaborators I've been working with here, Mariangela, Roman, Chai, for their invaluable work in helping me develop this project. So the motivation for this project is tied to the vast amount of data that we currently have access to in the astronomical community, especially with surveys like Gaia and now with JWST Online. We have a pretty unprecedented view of both our local neighborhood and across cosmic time. But in the coming years, as Euclid, Rubin, and Roman come online, we're going to get hundreds of petabytes of data of the local universe and pretty much everything in the universe we've observed in the past and much more that's new. And the observers have been working for years now to get their pipelines and analysis tools ready to accommodate this data, but the theoretical community has still a long ways to go before we have robust results that are ready to handle all of these different systems and unique things that we're sure to find. So this challenge is especially acute for my area of research, which is into what the particle properties of dark matter are. So there's a vast parameter space of potential candidates that reasonably describe what we've observed so far. And just one parameter of these models, the mass of the particle, can range over 50 orders of magnitude and reasonably describe our observations. And this becomes much more complicated once we include additional dark sector physics, such as interactions between dark matter particles, dark photons, or multiple dark matter species existing simultaneously. So what we need is some sort of framework that can efficiently span this huge parameter space, but also take advantage of the vast amount of data that we're soon to have. So the traditional method in this dark matter research is to take maybe a handful of kind of Milky Way-like galaxies and simulate them with some astrophysical galaxy formation model and include maybe a couple dark matter models that we think may be representative of a certain part of parameter space. But this leaves us with limitations in our results in that they're reliant on these particular galaxies we choose to simulate, the particular parameters of the astrophysical model, and it relies on these few samples of the dark matter parameter space are representative of the entire population that we're interested in. So what I've been working on here at the CCA is trying to take a new approach where instead of using this more traditional method where we only vary one parameter at a time, we can instead leverage our machine learning tools to vary not just one dark matter parameter, but start looking at these more complex models where we can vary multiple parameters simultaneously. But we can also just not use a couple different simulations, but we can run thousands of different simulations, each of which is looking at a different part of the cosmic web. And this modular framework is what we're calling dark AI. So this framework starts with models of the particle nature of dark matter. So the simplest model that we can write down is cold dark matter. So in terms of astrophysical scales, this model has 0 parameters. And it has done very well, from large-scale structure down to the properties of individual galaxies, but has been shown to be in tension, especially with some of the observed properties of satellites around the Milky Way. So this motivates us to look at some alternative dark matter models. So the first one we look at is warm dark matter. This imposes just one parameter into our model where we can now vary the mass of the dark matter particle and this can have effects on structure formation at astrophysical scales. So one thing I've been doing here at the CCA for this semester is now taking this a step further to include multidimensional models that can now start to incorporate some of this more complex physics into the dark sector and potentially provide a more realistic description of the dark matter in our universe that can potentially solve some of these small-scale tensions. So the next step is then take these different dark matter models and implement them in our simulations. So the first simulation suites that I started with were just n-body simulations. We ran over 1,000 of these simulations, each one looking at a different part of the cosmic web, and each one having a different prescription of the dark matter model. And we were able to show that with these machine learning tools, specifically convolutional neural networks, we were able to make much more robust results that didn't rely on a particular part of the cosmic web, and we're able to pick out much more signal than more traditional methods. So the next step was to include a realistic galaxy formation model. So we used the Illustrious TNG model, and this now allows us to include baryons in simulations and gives us much more data fields to explore and play around with. But what this also allows us to do is include variations in this parameter. Since these simulations have been shown to be at tension at small scales with observations, we want to be able to potentially change some of these feedback parameters to see whether the tuned properties of this model are causing these tensions. So now, instead of just varying the cosmic web and the dark matter properties, we're also varying properties of the baryonic feedback, all at the same time for each of these thousands of simulations. So one thing I've been doing here at the CCA is now extending this to a new suite of simulations, which are so-called zoom-in simulations, where we focus our computational power on Milky Way-like galaxies. And here we can run them at much higher resolution and really focus on the areas where these small-scale tensions exist and where the effects of the dark matter, these alternative models, are strongest. And this simulation suite now makes up the largest collection of simulated Milky Way-like galaxies with a realistic galaxy formation model that fully resolve all of the classical satellites. So this will give us a much more robust testing suite to understand whether these small-scale tensions exist, how prevalent they are, and then how these variations in dark matter and astrophysics can potentially alleviate them. So the next step is then, now that we have these complex data sets, we're varying many parameters simultaneously, each looking at a different galaxy or cosmic web, and traditional analysis cannot really capture all of this information, so we're utilizing different tools with machine learning. So the first one, with emulators, we've been able to look at different properties of these galaxies, such as the number of satellites around the Milky Way. And then using this technique, we can then look at each individual parameter, either the dark matter or the astrophysics, or each parameter within the dark matter model and the astrophysics, to see how these different galactic properties change as we change these different parameters. The next tool we've been using is convolutional neural networks, where we can give all of the information that we have in the simulation to these models, and they can tell us what the best possible constraints are that we can make on these dark matter models, and we can compare them to more traditional analyses to see if we're fully capturing that data and understand where we might need to look to produce better constraints. And then more recently, we've also been utilizing graph neural networks to take a more observationally motivated approach, where we can use observables or summary statistics of the satellites and their positions and compare these different methods to see which ones produce the best constraints, understand where in these upcoming data sets we should really focus our attention to make constraints on the particle nature of dark matter. So these three sections, the particle dark matter, our simulations, and our analysis, make up this kind of modular framework that we're calling dark AI, where we can really connect particle physics models to the things that we are going to be observing in the future. So here at the CCA, I've also been working on further extending each of these different parts. So for the dark matter models, I've been working on defining a section of the self-interacting dark matter parameter space that we could explore. And these interactions allow heat to transfer within the dark matter halo, and they can change structure and the dynamics of the internal structure of the galaxies, potentially solve some of these small-scale tensions. I've also started including the Ramses simulation suite into our dataset, and the Ramses code takes an entirely different approach to solving the numerical equations involved with structure formation and galaxy evolution. So we can, by combining or comparing our two data sets with the illustrious TNG model, we can gain a better understanding of how the numerics of our simulation are affecting our results. Then I'm also working on implementing a new suite of dwarf zoom-in simulations, where we can really target the galaxies that are at the most tension with lambda CDM and have the strongest impacts for these dark matter models. So with all of these different components, we have a very rich data set, thousands of different galaxies and various astrophysical feedback models and complex dark matter models, and we can really start to say with some certainty whether some of these small-scale tensions exist and how varying either the dark matter or the baryonic feedback models can help to alleviate them. So with that, I'll leave up my summary and take any questions. Thank you.
Thank you so much, Jonah. Questions? Case? Like in the slides that you talk about emulation, CNN, and graph neural network, what do you mean by emulation here? Because
yeah, so for this particular case, I'm talking about I give this emulator of just fully connected layers, and then I give the parameters that were used to train the model, and I have it infer the whichever galactic property, and then so it can interpolate between those parameters.
Okay, fine, cool, thank you.
This is great. My question is on this slide too. For these two plots for the predicted versus true warm dark matter mass, why do the error bars get bigger at bigger masses, and why are those so much harder to constrain?
Yeah, so as the particle, the dark matter particle mass increases, the simulations become more and more CDM-like, so that signal from the suppressed structure formation decreases. So there becomes much less signal in the simulations that we can resolve. So the machine learning models aren't really able to distinguish them as well, so larger error bars, and eventually it's unable to make any different distinguishing at all, and we get that kind of leveling off where it just thinks everything is CDM-like.
Adrian?
Thanks, this is super cool. So we have incredibly precise data now for stars and other objects within the Milky Way, and soon for nearby galaxy halos. But I think one of the things we're missing is the mapping from what are the killer distinguishing factors in the huge degeneracy space of possible dark matter models that produce interesting things we can measure locally to make distinctions. It seems like you might be able to answer that from a feature selection perspective with the simulation sets you have. Have you thought about that?
Yeah, absolutely. That is definitely something that we have started looking into and will definitely be pursuing. But yeah, the idea will definitely be to include, start off by including all the different fields to see what the best constraints are we can make, and then start winnowing that down to figure out what really the best ones are that we should focus our analysis on to make these constraints.
Cool. Thanks.
Let's thank Jonah again.
Okay, so hi everybody. First of all, thank you for coming and thank you for organizing the pre-doc program. It has been a wonderful experience, so thank you very much for that. And today I'm going to introduce you to the work that I've been doing here with Alice Pisani, and it's focused on the Roman Space Telescope and specifically doing forecasts for the CMB lensing cross-correlated with voids. So the Roman telescope will be a near-infrared and visible telescope that is going to be launched in May 2027. And it has the same dimension as the Hubble telescope, but its field of view is much larger. Although for large-scale structure, it's a bit small. The thing is that the interesting thing about Roman is that it's going to be really deep, and it's going to provide us with a sample of 13 million objects between the redshift of 0.5 to 3. But okay, I'm going to do forecast for the Roman telescope, but what I want to measure, why, and how. So the observable that I'm interested in is CMB lensing cross-correlated with voids. When talking about CMB lensing, I'm talking about the deviation of the path of the photons because of the gravitational potential of the large scale structure. And you can compute this deflection angle by solving the geodesic. So in this deflection angle, you have three quantities. Like you can describe this deflection by studying the convergence. So if you imagine in a more cartoonish way a bundle of photons coming towards you, you can see this deflection by the convergence or the divergence. It's expected that if it passes through a void, it will converge, and if it passes through a cluster, it will diverge. Then you can also have changes on the ellipticity, which will be the shear, and also you can have some rotation. So when I'm talking with CMB lensing, I'm just talking about CMB kappa, and this is the part that I'm going to study. On the other hand, well, the CMB lensing remaps because of changing the path of the photons, you are changing the distribution of energy, so you are remapping the maps of temperature and polarization. It's an unbiased tracer. It depends on the matter distribution, but it's a 2D observable. So to preserve the 3D information, we have the voids, which are these underdense regions in large-scale structure, and they are extremely interesting because in contrast with the galaxy clusters, they don't suffer from the non-gravitational non-linearities. So if we have some deviations from our standard models, these regions are expected to be like the best ones to study them because they are dominated by dark energy. So if we combine those two, then we will have this projected quantity of the matter distribution and the 3D information of the voids. So why I'm interested in this is, first of all, to know Roman's capabilities, which is an interesting fact in itself. But also there has been some tensions in literature regarding this observable. And it started with a similar observable, which is the integrated South-Wolf effect. It's really connected with CMB kappa, but it's not originated from spatial variation of the potential of the gravitational potential, but because of time variation. So if you think about the CMB map, you can remap it changing the path of the photon, so you have another energy distribution, but you can also have another energy distribution if you change the intrinsic energy itself of the photon, for example, with the expansion of the universe. So that's what is ISW telling us. So these studies start finding attention around 2 sigma. Some of them yes, some of them no. So there's kind of a contradiction in between them. And it seems that it's quite dependent on the void finder. So it will be really interesting to see with Roman, with a good signal to noise, how different void finders will affect the CMB cross-correlated with voice signal. So how I'm going to do it is through these 2 ingredients. I need a mock catalog to find voids, and a CMB kappa map. And what do I have? Nothing. So I need to construct everything from scratch, and I construct the pipeline that goes from building the Roman mock catalog then it goes to find the voids, and then finally I can measure the signal. To build the Roman mock catalog, I use the Agora simulation, that it has the same resolution as other Roman mock catalogs that are in literature, but those doesn't have CMB maps associated, so that's why I have to start from scratch. And this one also have plenty of maps available. So my first version of the mock matches the number density. In orange, we have the raw Agora simulation, and in green, after the subsampling. And we can see that we don't match perfectly the power spectrum, but this will be a first version, and then we will improve it with a proper HUD. So after that, we have our first version of the mock catalog, and we can start finding voids. We can do this in a 3D void version, like using Voronoi tessellation, and then merging different zones according to the density. Or we can do a 2D void finder, where you have your light cone. You just take a slice in Redshift, project it, and then in this density map, you find the voids. So we also have that in our pipeline. And finally, we have to measure the signal. First, we have to preprocess the CMB kappa map. So we do some smoothing and the removal of the bias. And then we stack the signal, which means that once I have my map and once I have my void catalog, I go to the map, I go to the positions of the voids, and I stack the images. Then I average that signal and measure the profile. For the uncertainties, it will be the same procedure, but instead of the original kappa map of the simulation, I will generate a random realization, which will be produced by implementing a map with the power spectra of the original map plus instrumental noise. So that we can test the null hypothesis and see how likely is that we get the same signal just by random fluctuations. So we have that, and we just start running some first tests. For example, this is with the 2D void finder. We just split in different redshift chunks with the same number of voids, and we can see that we detect a signal, although with high uncertainties. If we just increase the number of voids, then the uncertainties decrease a little bit, but it's still really significant. With 3D void finders, we have a smoother signal, although between them they are consistent within the error bars. So it seems that a 2D void finder could be more interesting. But we need to try to maximize the signal to noise ratio, because now it's like a first test, and we need to understand these uncertainties. And it's probable that it's because we did a first cut to just consider the larger and more underdense voids. And this could be not ideal for CMB lensing, because it seems that it's caused by the most tiny density fluctuations. So probably we'll need to play a little bit with the sample of tracers that we are considering, voids, sorry. And so now that we have the pipeline, the future work will be to refine some of these steps. First of all, finish the halo occupation distribution to match the number density, but also the clustering, like the power spectrum or their other higher statistic properties. Then in the find voids part, we have to check the consistency between void finders and make them more computationally efficient, because for really dense samples it takes a lot. And of course, maximize the signal to noise, playing with different void types and void definitions. For example, you can have a void in void or a void in cloud, which means that you have a void in an underdense region, or you have a void surrounded by galaxies. And if you mix all of these signals, you maybe have a smoother one. You are not maximizing it. So we are going to check all these. So yeah, some take-home ideas. We present here the first pipeline for the CMB kappa cross-correlated with voids for Roman, built from scratch. Roman will mean a change of paradigm in CMB lensing and also for the void studies. And find the best configuration for a higher signal to noise maybe could alleviate some of the tensions I talked before. And finally, we will be able to reach the smallest scales with voids, because they are more linear regions, and this will be extremely interesting for the future. So thank you very much.
Thank you very much, Mark. Questions? When you say computationally more efficient, that's like everyone knows that's my keyword. What is the scale of computation that you are at now, and what would be the desired level that to make it more efficient?
So for some of the void finders, when you use like a super dense sample as this one, the memory crashes. So it's not my code, so I don't know what is exactly the problem, but you have to tune a lot of parameters, like the divisions of this, of this void finder, in order to not crash in memory, and seems really sensitive. So it seems that having these upcoming surveys of with really dense galaxies is maybe a problem for the actual, like the current void finders that we have now.
Adrian?
Lucia, you can ask me. All right. This is a dumb question because I'm pretty naive on this topic, so apologies for that. But I assume that it's probably easy for the 3D void finders and even the 2D. There's probably some bias in thinking in 3D, in that it's easier to find a void because of redshift errors if it's already on like a line of sight that's less dense or something. You know what I mean? Because if you had like a dense thing in front of the void and a dense thing behind it, then redshift errors will scatter things into the void, and you might not call it a void or something like that. Does that bias have any implications for the statistics?
If I understood correctly, like when you stack the signal, you will have other things in front of the. Are you telling me?
I'm thinking of just even identifying something as a void. It's probably easier to to identify a void if it's overall in a line of sight on the sky that's less dense than other neighboring parts.
That's how the 2D void finders work, because you are projecting, so you are taking regions on the sky that are in this elongated way less dense.
Right.
But with the 3D void finders, you just have all the positions, so you don't take into account that.
So the redshift errors are good enough that that doesn't the thing that like the line of sight doesn't affect you too much.
So it seems that having a 2D void finder maximizes the signal just because of this line of sight effect. But with the 3D void finder, you are not taking into account nothing, like the.
Okay.
If I understood, sorry.
Okay.
Also, a lot of the surveys will be with the prism and the spectrograph, so it might not just be photometry
To get the redshifts.
Mm-hmm.
Okay.
Yeah,
Got
it
it.
will be spectrograph.
Cool. Thanks.
Okay, let's thank Mara again.
Next up, we have John Soltis. Congratulations, John.
Thank you. All right, so I'm John Soltis. I've been a pre-doc here. I'm normally a graduate student at Johns Hopkins, and I've been working with Lehman Garrison on testing the robustness of mass accretion histories in scale-free simulations. So why do we care about mass accretion history? So mass accretion history is correlated with a lot of other halo properties of interest, for example, concentration. So in the case of galaxy clusters, what I normally work on at Johns Hopkins, mass accretion history also drives galaxy cluster dynamical state, which then in turn biases mass estimates of galaxy clusters, which then in turn biases cosmological constraints that you can derive from galaxy clusters, especially S8. So there have been a lot of efforts to characterize mass accretion history, and most of them rely on using simulations. So as an example of that, this bottom panel here is showing simulated observations of clusters in the Millennium TNG simulation for some research that I've been doing. So wouldn't it be good to know then if the mass accretion histories that we're relying on in these simulations are actually reliable? So to approach this question, we decided to use Abacus, which is an n-body code. So I've been talking about galaxy clusters and their effect, or the effect of mass accretion history on their dynamical state. But you would think then that I would be really interested in what's going on with the baryons. But unfortunately, testing the robustness of mass accretion histories or any other properties in hydrodynamic cosmological simulations is actually pretty difficult. And so using Abacus gives us some advantages. So some of the advantages are that Abacus, you can generate large simulations more easily. So the simulation we're using has 4,096 cubed particles. You can generate many different cosmologies, although here we're going to restrict ourselves to one class of cosmology. Within that class, we can generate variants by changing the spectral index. And conveniently, there's research into the connection between mass accretion history and cosmology directly that uses the Abacus Summit suite of simulations, which obviously uses the Abacus n-body code. So basically, the way that I look at this is that this is sort of a simplified first step towards getting a broader understanding of the robustness of mass accretion histories in a larger set of simulations. Because the test that we're doing here, we can also apply to other n-body codes, or we can apply to the dark matter components of hydrodynamic cosmological simulations to get some sense of an upper bound of robustness. OK, so what is the test that we're doing? So we're relying on something called a scale-free cosmology. So using a scale-free cosmology, we can generate a scale-free simulation. A scale-free simulation is a simulation with an Einstein de Sitter background. So this is a mass-only simulation, and a power law-like power spectrum of initial fluctuations. And coming from that, we end up with only one relevant physical length scale, which is this scale of nonlinearity. And the takeaway here is that for any dimensionless halo property, you can rescale that property by this physical length scale, and then that property should become self-similar. And so what that means in practice is that a rescaled halo property doesn't show any time evolution. So an example of that is that the mass accretion history of small halos or low mass halos at early times is the same as the mass accretion history of high mass halos at late times. And the reason for that is that small or low mass halos at early times and high mass halos at late times, when rescaled by this length scale, which you can turn into a mass scale, are the same within these units. So we don't expect the mass accretion history to change. And so the advantage of this kind of test, then, is that we can take a look at the simulation, and we can see where it follows this behavior. And where it deviates from this behavior, we can say that it isn't reliable, that the simulation, or perhaps the halo finder, is introducing some non-physical length scale, and that we shouldn't trust the result. And this allows for a more absolute probe of robustness, as compared to generating multiple simulations with different hyperparameters, and then looking at the results. So I mentioned this briefly, but we're also interested then in how the choice of halo finder affects the results. And we take a look at two halo finders here. Rockstar, which from previous work doing a similar test on the halo mass function, we think is going to be more accurate. And also, I know from experience, takes much more time to run on our large simulation. And Compasso, which was designed to run simultaneously with Abacus. But the trade-off here is that it's less effective at preserving self-similarity. And so we want to see how the bounds of robustness change depending on the decision that you make with Halo Finder. OK, so the last thing that we need to do before getting into the results here is define what I mean by halo mass accretion rate. So how we define a halo mass accretion rate here is we define the average change in mass of a halo or a set of halos within a mass spin to their most massive descendants the next time step. And so what we end up with is a mass accretion history that's a function of both your choice of mass spin and your time step. And when we do this rescaling by this mass scale of nonlinearity, effectively what we're doing is we're changing where we're taking this average. And that's how we're getting this self-similarity property. So here's a visualization of this. So on the left here, I'm showing a plot of mass accretion history versus mass. And on the right, I'm showing a plot of mass accretion history versus this rescaled mass. And each individual line here represents a time step, and they're also shown in a different color. And you can see that comparing the left to the right, at least for the majority of the halos that we're looking at, when you're using mass units, they don't line up. And then when you use the rescaled units, now they lie on top of each other. And so what that's telling you is that in rescaled units, there's no change in the mass accretion history, especially at, like, say, a value of 1. And then the other interesting takeaway here is, of course, the simulation and the halo finder aren't perfect. And so when you go to these very low mass halos, you don't see the self-similar property. So there are some non-physical length scalars being introduced, and the results are not robust. OK, so what we need to do next then is come up with some quantitative way to understand whether or not we're converging to self-similarity. So the way that we do that is we sort of change the way that we're looking at it, and we plot mass accretion history versus time on the x-axis. And so now each line represents a different rescaled mass bin. And when we look at it this way, the way that we see self-similarity is just a flatness, right? So the mass accretion history for a given rescaled mass bin is not changing with time. And ultimately, what we do then is we have this convergence metric. And I won't really go into the details here, but what you need to take away from this is that we're looking for regions, continuous regions in time of flatness. And then we're coming up with some calculation of a % deviation from flatness within that region. And so once we do that, we end up with a plot like this, which is showing different % convergences to self-similarity in the space of time on the x-axis. And then here, this is actually particle count per halo. So first of all, I want to point out that we're only considering regions that are greater than 1,000 halos to get our statistics. But the second thing I want to point out, and this is the results for Rockstar, is that you have this really large region of high convergence for Rockstar. It's mostly at late times, but it covers a wide range of particle per halo parameter space. The other interesting thing that you see here is there is this temporal evolution of convergence for low mass halos. So we think that on the very low end, this might be a transient convergence. And then we lose some convergence to self-similarity sort of at other early times before, as the simulation evolves, getting it back again. And at the very far end there, that loss of convergence we think is being driven by our choice of convergence metric. And so if you change the width of a region that you're looking at, you can change where that kind of cutoff is coming in. And so generally speaking, we can say that there's roughly speaking, a bound of around 100 particles per halo that you need for convergence, although at late times, obviously, it's doing much better than that. And we can say that there's an upper bound of around 100,000 particles per halo for convergence. And this is being driven mostly just by an availability of halos. So it's possible if we had more halos in the simulation that we could say that there's better convergence, but we don't know that based on this procedure. And so looking at Compasso now, you can see that there's a similar located region of high convergence, but it's not as good of convergence, and it's obviously also not quite as large. And again, stepping back and talking about it more generally, we can see that there's this lower bound of around 100 particles per halo where you get convergence, although it's not as good at the low end as Rockstar was. But now there's also this interesting upper bound of convergence at around 10,000 particles per halo. And that's not being driven by an availability of halos in the simulation. That's being driven by something in the halo finder itself, which we think has to do with the procedure that it has for identifying halos. And it's fairly strict in its cutoff, so it's breaking up these large mass halos. So it's introducing, again, a non-physical length scale. So just the takeaways here are that mass accretion history is important. It influences a lot of halo properties of interest. It influences mass estimates for galaxy clusters. And of course, obviously, it also influences cosmology. Abacus is useful to solve this or to investigate this problem because it can generate large simulations with a lot of different cosmologies. But most importantly, you can use it to do this self-similarity test. And for the results specifically, we found, kind of as we expected, that Rockstar demonstrates better convergence than Compasso. Compasso is more limited on the high end of halos because of its own procedure, whereas Rockstar is more or less limited by the simulation. And then both of them, very roughly speaking, have a bound of around 100 particles, although at late times in Rockstar, you can get to a much lower limit and still have an accurate mass accretion history. And so for future work, this test can be applied to other n-body codes, and it could also be applied to dark matter codes related to hydrosims. And it could also be applied to different properties, too. You're not just restricted to mass accretion history. So there have been other papers looking at this, like I said, for halo mass function as well. So if you're interested in some property and you're using some cosmological simulation, this is a good way to test, in a more absolute sense, how robust that simulation and the results that you're deriving from it are. Thanks.
this work? Can you hear me?
Yeah.
Oh, okay. I've been gotta get bit confused. What exactly is evolving self-similarly?
I'm sorry?
What is evolving? What is self-similar exactly?
Oh, so in this case, it's the mass accretion history itself. So any property of the simulation you can define to be self-similar in this kind of cosmology. And in the sense that I was talking about it, in the sense that it's not changing with time when you do this rescaling by this spatial coordinate, or this spatial length, if that makes sense.
Cool. So do you have any, like, I guess, takeaways for how to best use these halo finders? You know, is it maybe that Compasso is great if you have relatively low resolution, huge simulations, and Rockstar is really worth the effort with smaller particles?
Yeah.
Or do you have any insights from that? Yeah.
Yeah, I mean, I think that itself is a good takeaway. So when I was using Rockstar on this simulation, Rockstar itself took some time to run, but then especially running consistent trees, like the sort of the cleaning procedure, took like over a week to run with quite a few cores. So if you're computationally limited or you're using a really large dark matter simulation, you're probably going to want to be careful about using Rockstar, even though it gives you this really strong accuracy. So if you're trying to do a lot of simulations more quickly, I think Compasso is, I mean, it's sort of designed for that, so it performs better there.
So I wanted to follow up. I have a lot of questions, but so as someone that does these kind of simulations, I'm interested in takeaways, like much like Lucia was asking. The kind of lower bound on the convergence, that's unsurprising because people are normally like, well, we need to have at least 100 particles to call something a reasonably resolved galaxy. But the ceiling on convergence that you found, that's something that's like a bit scarier because my naive interpretation is that means you could miss some really large halos, especially using Compasso. And I don't remember, for Rockstar, you said you couldn't really tell because you don't have enough halos.
Right.
But to me, I feel like that's something that's really important, is to kind of determine, if I'm using Rockstar, could I be missing some clusters because of the halo finder, in my simulation if I get above 10 to the 5, 10 to the 6 particles. Do you have ideas for, how could one go about testing this? You have to just run larger simulations and do the same kind of test? Because I feel like if this is a problem, it seems to be with Compasso, that could be scary.
Yeah, so I think that if you're really interested in very large halos, at least right now, and maybe this isn't like a nice answer, but I think that you probably do need to run a larger simulation with more particles if you want to be really confident. I mean, we sort of imposed this 1,000 halo limit. Maybe if we were more clever, we could test the robustness of the results sort of into these smaller halo count bins. And at least with Rockstar, I mean, we didn't see any evidence that it was losing convergence on the high end, really. But I mean, you would imagine that as you have less halos at that size, unless that drop off is physically real, then you're probably losing some mass accretion history accuracy as well, or any other property that you're interested in. Yeah, so I would say that, yeah, if you're really concerned about these really large mass halos, then yeah, this is something that you do want to keep in mind.
All right, well, thank you very much. Let's thank John again. Yeah, sorry. John, microphone.
Oh, yeah.
I do that every time I give a talk, so. All right, are you good? Our last speaker is Tom Wag. Congratulations, Tom.
I'll treasure it always. Wonderful. Well, lovely to be here. Lovely to be talking to you. Thank you for sticking around to the end. I do appreciate it. So today, I'm going to be talking about integrating binary evolution with galactic orbit integration and all sorts of things. And if you know me, you know I love a good binary. And the good news is the majority of massive stars are going to be formed in binary systems. Over 70% of O stars are going to exchange mass at some point. You have, a couple that are effectively single, but lots of them are going to end up, having some form of binary interaction. And this is important because those massive stars that are in binaries are going to play a very crucial role in galaxy evolution. If you don't have these stellar winds or these supernovae we've heard in some of the earlier talks, you don't end up producing the sort of galaxies that you want to see. Without that feedback, you can't really reproduce this observed galaxy population. So it's important that we understand this. The thing is, binary evolution still remains highly uncertain in many key parameters. If you look at some of them, it's like over several orders of magnitude, and at that point you've got some problems. You could be looking at common envelope evolution, where you've got the cores of two stars inside one common envelope. How efficient is that? How easy is it to eject that envelope? I don't know. How strong is a supernova kick? You have some asymmetry at the onset of some supernova. You get a kick, gives you some velocity. What's the magnitude of that? How is it distributed? Is it bimodal? Lots of questions, lots of uncertainty. We want to come up with ways that we can understand this better. And so one of the ways that we could consider doing this is by looking at the positions and the velocities of some of these systems. Because you can imagine that for single massive stars, these are stars that don't live for a very long time, and if they don't have very much initial velocity dispersion, they're going to stay pretty much where they are, pretty much with the velocity they started with. But with a binary system, you can then start imparting some quite large velocities. If you've got some binary where you've got a slightly more massive star with a slightly less massive star, and it's evolving along, the first one goes supernova. Let's say it becomes a black hole, and it goes off with that supernova kick that I was talking about, and then that disrupts the binary, and the other star is going to fly off with whatever the orbital velocity was at the point at which it disrupted. And so in these cases, you can find stars and compact remnants that are found at very large separations from where you might expect, and they'll have reduced spatial correlations with one another and with traces of gas that you might expect them to be associated with. And so what we need is a way to model this and understand it a bit better. And that's where I come in. And so what I've been doing is kind of trying to design the theoretical infrastructure for modeling these things by creating a new code that I call Cogsworth, which is not an acronym. I just think it's fun to say. And so this basically has two core components to it. First is the population synthesis. So you want to be doing all of your binary stellar evolution rapidly. And for this, I use Cosmic, which is Katie Brevik's code, who was here and now isn't, which is sad. But I combine this with Galactic Dynamics, with Adrian's Gala code. And so between these two, I can do all of my stellar evolution. I can work out when the supernova happened. And then I can be integrating their orbits through a galaxy and also seeing where they end up and what velocities they have. And the nice thing is, it's quite flexible. So what you can be doing is changing your binary physics assumptions. How efficient do you want to make that common envelope? How strong are you making those supernova? You can change all of that. You can change how you sample your initial population. What are you using for your IMF? How are you setting the initial orbital periods? All sorts of things like that. You can change all of that. And then on the galaxy side, you can change the star formation history. Where are your stars formed? When are they formed? With what metallicity? All of that you can change, lots of parameters. And then the galactic potential. So what are we looking at? Is it a Milky Way-like galaxy? Is it a dwarf galaxy? How is the potential shaped? You can change all of this. And one of the other things I've been doing while I've been here is kind of working in the fire and the Changa simulations as initial conditions to that. So I have I didn't put their names on here or their faces because I didn't ask, but Matt, Chris, Alison Brooks, Akasha Cruz, all very helpful in getting this set up for me. Well, helped me set it up anyway. And what this does is you take your hydrodynamical zoom-in simulation. That has a bunch of star particles, which you can use to sample binary stellar populations, and that can set your star formation history. And you can also work out what the galactic potential is based on some self-consistent field method, and you can then work that all in. And that gives you your full simulation. And then at this point, what you can get out is the usual sorts of things from population synthesis. You can get your kind of rates, you can get distributions of what the masses are, what the orbital periods are, but you can then also now get the kinematics of all of the massive binaries and the compact objects. Where are they? How are they moving? And taking all of that together, you can then convert that to an observable population. So we don't just want to look at what's intrinsically there. What we want to see is, what is the magnitude in this particular Gaia filter? And you can do this with Cogsworth. And so I encourage you to go and check out the documentation. I have lots of tutorials now, lots of examples. It's all on there. Oh, and there is a thing as well where you can press a button and it will give you the citations of the papers that you need based on what you have used. So now I will tell you what I have been using this tool for while I've been here at the CCA. And this is looking at the timing and location of supernova and how this is going to change the way the feedback works. So say you've got this situation where you've got some very dense molecular cloud sitting in some maybe more diffuse region, and you have a single star that's just sitting there, and it's a single star, so it's boring, and it just goes supernova where it is. But now say you've got some binary star, and it's in some system, and something else goes supernova, and it flies off with some velocity all the way over here, and then goes supernova there, in something that is a bit more diffuse. That's going to have very different impact on the feedback. It's happening in a very different region, and, well, it'll be different. So the thing is, the way that it's currently implemented in most of these hydrodynamical codes is that the subgrid physics that is assumes single-star evolution. If you look at any fire or Chang'e thing, what they assume for the type 2 supernova rate is that it's based on single-star evolution. If you look at fire's type 2 supernova rate, it's basically a step function, and it goes between about 3 and about 37 million years. Remember that. It's going to be important. Now, binary evolution can delay supernovas. So instead of them happening and then immediately stopping at about 37 million years, they can extend out to like 200 million years. So you can have a lot of delayed feedback happening in your galaxy. And at the same time, the supernova can be displaced from where you might expect to find them. If you've got, as I was saying, some supernova from a companion, you then get flung off to some far outer reaches of space and then go supernova, that's going to be very different. And so what we set out to do was basically quantify this and investigate how things happen. And so I'm just showing you one of the simulations here, which is based off the Fire M11H, which is just one of the dwarf galaxies from Fire 2 simulations. And what we did was take every star particle that's formed in the past 150 million years, and from those, sample binary stellar populations, and then you end up with about 2.5 million binaries. You take those, you put them in the galactic potential based off this galaxy, you evolve them around until present day, all of the stellar evolution, all of the galactic evolution, and then you end up with a galaxy. And what it looks like, I'm going to show you a face-on and an edge-on version of this. And what I'll first show you is if you just do this without accounting for all of the binary physics that could move things around. And so you can see in the kind of face-on here, edge-on here, you can see you've got some sort of spiral arm structure. You've got some sort of gaps in it. You can see small-scale variations. But then you turn on Cogsworth and you account for all of this binary physics, you can end up seeing quite a different picture, where all of your kind of, whether they are remnants or stars getting flung far away, you can get the gaps sort of filled in. And you get a very different picture because of that, and that's going to change how the feedback works. And so if we now look at first the timing of the supernova. So remember, it's currently cut off at like 37 million years. You'll note from the x-axis that this goes on for a little bit longer. And I'm going to show you how this supernova rate is varying over time. And I'm going to show you a series of stacked histograms. The blue ones are primary stars in binaries. The green ones are secondary stars that are in binaries or were in binaries. The gray ones are the binaries that are so far apart that they basically didn't talk to each other. They're effectively single. And then yellow is something where they have got too close together. They've ended up merging and then gone supernova later on. And so what this looks like is something like this. So this dotted line is where it currently cuts off when you assume single-star evolution. But you can see there is a long tail all the way out to 200 million years. And so what are these things that are taking a really long time to go supernova? Well, most of the time, it's either your green or your yellow ones. So these are things where you've had, OK, let's take the merger products. These are things where they've been initially less massive. They take longer to evolve. And so they're just kind of trundling along. Then they merge, and then they go, oh, now I'm massive enough to go supernova. And you can end up getting supernova going on at like 200 million years rather than 37. And so the timing is being strongly affected by what happens with the binary physics. But the other thing to look at is where do these things happen? So the location of the supernova. So what I'm going to show you now is where the distribution of the supernova, but as a function of the distance from the parent cluster. So you've put these things in some, you put these things in a cluster. The cluster has been moving along. The star has also been moving along. And I'm showing you the distance between the supernova and the position of the cluster at the time of the supernova. And so you'll see this is a log scale. It's going out quite far. And so instead of putting things exactly where the cluster is, which is currently done for all of this feedback, you can see this is extending very far. You can see it peaking around 100 parsecs and going out to even several kiloparsecs based on what's going on. And this kind of, if you look at a time evolution of this, it kind of pushes out to the right as you're going. You can see the yellow ones, the merger products, as we noted, are taking longer to go supernova. And so the cluster has longer to dissolve, and so they can end up further away. But the green ones are fun, because these are the situations where you've had a primary star that's gone supernova, disrupted the binary, the secondary has been flung off with whatever the orbital velocity is, flown very far away, and then gone supernova. And so you can have feedback happening at really large distances. So that's quite fun as well. And so what I will do is just leave you with my takeaway points and just say thank you to all of the wonderful people here. Like, I have had a great time interacting with everyone in the cohort and all in the various groups I've been involved with. All of these lovely people who've been meeting with me every week and helping me go through all of my questions. It's been great. Hope I can come back soon.
Thanks very much, Tom. Yeah, Jared?
Yeah, great talk. Really cool stuff. I was taken by the last plot where you showed kind of different types of stars exploding in different places.
Yeah.
Right? So primaries probably were donors, secondaries were probably accretors, and if you think of it in those terms, I would expect there to be differences in the supernova rates of like type 2b or 1b sort of stripped envelope supernovae versus farther away. Have you thought much about the distributions of the type of supernova populations that transient observers might be able to point to?
I haven't, but that sounds very interesting.
Okay.
Yeah, I will definitely be thinking about that now. Yeah, cool.
Very cool. Also interested in this plot. Do you do this study like single cluster by single cluster, or are you doing it's a whole galaxy, right?
Yep.
So how often do you find that one of these supernovae like wanders over to some other cluster to mess up something else that hasn't quite formed?
I haven't checked, but I could check. I do them all at once, so I could check that. Yeah, that'd be cool.
Yeah.
Maybe more computationally annoying if I have to check all of the other ones, but I'm sure I could do some region close to it, yeah.
But yeah, because it'd be because obviously triggered star formation is a big topic, and so if you can show that it is a wandering supernova, you could actually do this quite effectively.